All right, so in this video, we're going to take a look at some of the classes and interfaces in the JDK that are related to queues. But before we do that, I just wanted to say that the time complexity for a queue that's backed by an array will, of course, either be constant or linear. It'll be constant, O of 1, if we don't have to resize the array, and linear if we do. Now, I'm not going to go through the implementation of a queue with a linked list. A linked list, a doubly linked list, is perfect for queues. I mean, you add items to the tail of the list and you remove items from the head of the list. It's perfect. And all of the operations, the add, remove, and peek operations would be performed in constant time. To implement the queue, we do exactly what we did when we implemented a stack using a linked list. We'd wrap the linked list class with some other class that we would call queue, let's say, and we would just expose the add, remove, and peek methods. And so I'm not going to go through that again because it's simple to do. And if you need to review what we did with the stack, you can go ahead and watch the video about backing a stack with a linked list. And the only difference with a queue would be that instead of exposing the push, pop, and peek methods, you would expose the add, remove, and peek methods. Okay, so with that out of the way, let's take a look at some of the classes in the JDK. Now, the JDK has a queue interface that we can use, and as you can see, there are quite a number of classes that implement this. Now, if we take a look at the methods, we'll see there's not that many. There's the add method, the peek method, and the remove method. There's also poll. It says it retrieves and removes the head of this queue or returns null if the queue is empty. So with remove, I believe if the queue is empty, let's check this, you'll get the no such element exception. So the difference between poll and remove is in the remove case, if the queue is empty, you get an exception. And in the poll case, if it's empty, you're just going to get a null. There's also offer, and you'll say here it inserts the specified element if it's possible to do so without violating capacity restrictions. So this returns a Boolean. You'll get a true back if it was able to insert the element and false otherwise. So queue isn't a very complex interface. It's only been in the JDK since 1.5, so it's rather new. And as we just saw, the add, remove, and element, they're using element for peek. That they throw an exception if you can't complete it, and in this interface, offer, poll, and peek will return a special value. So when we implemented peek, we were throwing an exception. So we kind of implemented the methods that are in this column. Didn't use the same names because we weren't implementing queue. And the methods in this column don't throw exceptions. If they can't do something, they'll let you know by returning a specific value. Okay, so here's array blocking queue. And if we go to that one, we'll see that it's a bounded blocking queue backed by an array. And of course, the queue orders elements FIFO, first in, first out. Now, this is a bounded blocking queue, so it doesn't resize the array. It says once created, the capacity cannot be changed. Attempts to put an element into a full queue will result in the operation blocking. If a thread tries to add an element into this queue, it will block until some other thread has come along and taken an element out of the queue. And the same goes for remove. If you call remove and the queue is empty, then you're going to block until something's added to the queue. And if we take a look at the package, we'll see that this is in the java.util.concurrent package. So it's meant to be used when more than one thread is going to be accessing the queue. So often this type of queue is used in producer-consumer scenarios. So let's say, for example, messages are being passed over a network from a producer to a consumer. The producer or the sender adds messages to the queue, and the consumer or receiver will remove messages from the queue. Now, if the producer, the sender, tries to add a message to the queue and the queue is full, it's going to block until the receiver has removed a message from the queue. And of course, if the receiver goes to take a message off the queue and there's nothing there, it's going to block until the sender has sent another message. So this producer-consumer scenario is a perfect scenario for FIFO behavior, when you want the messages to be read in the order that they're sent. Right? You can use a queue, you add messages to the end of the queue, and at the other end, the receiver is going to be taking messages off the front of the queue, and so the receiver is going to be processing the messages in the order that they were sent. And so this implements the queue interface. You'll see there's also a blocking queue interface, and it implements that as well. Now, if we go back to the queue interface, we'll see there's another class called concurrent linked queue. And this is an unbounded thread-safe queue based on linked nodes. So this is based on a linked list. It's also in the java.util.concurrent package because it's meant to be used by multiple threads, but you'll notice that this one is using an efficient non-blocking algorithm. And so it doesn't block. And one other thing to note is beware that, unlike in most collections, the size method is not a constant time operation. Now, normally, to get the size, the number of steps doesn't depend on the number of items in the list because you're usually just keeping a counter. But because this implementation of a queue can be accessed by multiple threads, determining the number of elements requires a traversal of the elements. And so that's not going to be a constant time operation. So let's go back to the queue interface. And as I said, there's a number of queues here. And just like with the list, if you want to implement your own queue, you might want to start with the abstract queue class because that will have implemented the methods for queue and you can just override the ones that you want to customize. Now we'll see that the plain old linked list class implements queue. And as I said, we can wrap this class just as we did for stacks and only expose the methods that are related to queues. And before we leave this topic, I'll leave you to explore the other classes on your own. I want to look at the DQ interface. So we saw this interface when we were looking at stacks, and a DQ supports insertion and removal at both ends, and DQ is short for double-ended queue and is usually pronounced DEC. And so I've actually been pronouncing it wrong. It's one of those things that I don't say very often, and I probably have it in my notes somewhere to pronounce it DEC. So there you go. It's pronounced DEC. And there's a few tables down here that summarize how you work at the head, how you work at the tail, and then a comparison of the queue and the DEC methods. Now I know to say that is DEC. Now, as we saw when we looked at stacks, Java has an array DEC class right here, and this is a resizable array implementation. So there's no capacity restrictions. Now this class was only added in Java 1.6, so it's pretty new. And because it implements the DEC interface, it has methods for add first and add last, because with a DEC we're allowed to add at the beginning and the end of a queue. And of course linked list also implements this DEC interface. We saw that when we were looking at linked lists. So if you have a situation where you want a queue that you can add and remove items from both ends, then using one of the classes that implements the DEC interface would be good for you. Queues are used way more often than double-ended queues. So that's why we went into more detail about queues, and that's pretty much all I'm going to say about DECs or double-ended queues. So I'll see you in the next video.